In today's class, we have to discuss different stick and layout diagrams of different MOS devices. So already we are designed. So we have some knowledge about how to design a CMOS circuit or NMOS circuit by seeing proper uh, Boolean expression. That means when we see expression, that means the output expression, if the y is equal to a plus b whole bar, or y is equal to a plus b plus c whole bar, or a into b into c whole bar, or ab plus ba whole bar. So when we are observing this type of logic expressions, so we have, by using some of the rules, that means we have mainly two operations when we see the Boolean expression, Boolean logic expression. So for any variable that may have that from one variable to another variable, we have two operations. That means one AND operation and OR operation, and OR operation in between one variable to another variable. So by seeing that and or operation, so we have to design any type of circuit by using by using the MOS transistors, by using the MOS transistors. So here we have, in today's class, already in the last class, we seen what are the different colors represent to different layers. In today's class, we will see, by using those colors, we have to design a proper stick diagram, stick and layout diagram, uh, by using whatever the color representations we learned in the yesterday's class. We learned in the yesterday class. So in today's class, we'll see, first of all, we see the circuits designed with help of the NMOS transistors, only NMOS technology. So by using NMOS technology, so first we have to look into how that will be designed. So after that, the next one, how to draw a stick diagram from the designed designed MOS transistor diagram to the stick diagram. So after the stick diagram to how to we will draw a layout diagram from the stick diagram, So this is the step-by-step process. So wherever in your examination also, if the question is asked, so design a layout diagram for NMOS inverter, or design a stick diagram for NMOS inverter, it may be NMOS technology or it may be CMOS technology. So whatever the question you have to seen in your question paper, so you must and should start with uh, this MOS transistor level design first itself. So first you have to draw transistor design. So after the transistor design, you have to draw the stick diagram. So after that, you have to draw the layout diagram. So if those in question paper you have only asked only stick diagram, so at the time you have to draw a transistor level diagram and the stick diagram. So in case in your question paper the question is in in terms of layout diagram, so at the time you have to draw these three designs. That means three designs. Those are nothing but, one is the transistor design, and second one is the stick diagram, and another one is the layout diagram, and another one is the layout diagram. So in this way we have to uh, answer for these questions. So in today's class we will see what is NMOS inverter. So NMOS means so we have to use only the NMOS devices, only the NMOS devices to represent the inverter functional. So in NMOS we having depletion mode category and the enhancement mode category. We have two type of transistors. So then basically is for the simple inverter, the logic expression is y is equal to a bar. Y is equal to a bar. So that inverter will gives whatever that inverter maximum that have one input. For the inverter they have one input, so from that one input at the output side, the output of that inverter is the complement of the input, the complement function of the input. That means y is equal to a bar. So if we are considering input is a, so uh, we get the output is equal to y is equal to a bar. Y is equal to a bar. So here that inverter functionality will be implemented with help of only NMOS transistors. Only NMOS. That means in the pull up case, we have to use the depletion mode transistor, and the pull down case, that means with respect to ground, we have to use enhancement mode transistor in down part. In upper part we have to use a depletion mode transistor that will be connected to VDD voltage. So for inverter it will consist depletion mode. So what is the indication of depletion mode will be, so from drain to source terminals, drain to source, there will be a uh, thin thin widely that will be extracted, or thick line will be drawn in between from drain to source regions, so that is the indication of uh, that is the difference between diffusion mode transistor and enhancement mode transistor. So in whenever we are connecting series manner, so then it will be works like as a inverter. So this NMOS, the two depletion mode transistor and enhancement mode transistor will we have to connected in a series manner, or we have to connect with each other. So the output will be works like as a inverter. That means, so if the a is equal to 1, if the a is equal to we will see the operation in two cases. So if the a is equal to 0 and the a is equal to 1. So if a is equal, in the first case, if the a is equal to 0, so at the time the enhancement transistor in off condition, enhanced transistor will be off condition. So because for the enhancement mode transistor we give the 0, so there will be no channel. So the electron will be doesn't flow from one side to another side. There is no channel. So due to that there is no channel formation in enhancement mode transistor. So that will not uh, active, or operation did not performed by the transistor. So it will be in off condition. So off means that enhancement transistor will be acts like as a open switch. So there is no flow from VDD to ground. So because of that reason, so in the same case, if the input is equal to a is equal to 0, so in respect of the input in the depletion mode transistor, the channel will be formed. That means whenever the channel is formed, the electron flow will be started in from one region to another region. So due to that reason, the depletion mode transistor will be non-condition. So on means whatever we applied the VDD voltage, so that will be come out at the output terminal. So that VDD voltage will be come out at the output terminal. That means Q is equal to VDD. Q is equal to VDD. So VDD is equal to, in logic terms, VDD is nothing but logic logic 1. So that means whenever the input is low, output will be high. So already we know this operation. So overall operation. So from this circuit or from this uh, transistor diagram or transistor design. So from this transistor design, we have to draw a stick diagram. We have to draw a stick diagram. So listen carefully. So here for VDD, for VDD and the VSS, so we have to use a metal. So metal will be represented with blue color. So horizontally we have to draw for the VDD purpose and the VSS purpose two colors. We blue color metal. We have to use at the upper part and the bottom part is blue color clear. So after that, so in this depletion mode transistor, so we have NMOS transistors. So in these both transistors, we have to use the diffusion is N diffusion. So N diffusion. So N diffusion will be represented with green color. Green color, clear. So green color. So up to one part for NMOS depletion mode transistor, we have to take in green color. So in the below also we have the NMOS transistor. So the same green color will be extended to up to ground level, up to ground level. So we fulfilled the 10 mass transistor with N diffusion. So green color is taken. So here we have to work there will be we have to that stick diagram will work like as a transistor. So at the time we have to use the polysilicon. Then the polysilicon will be crossed with diffusion material and the polysilicon material. So then only that will be acts like as a any type of transistor, either it may be NMOS transistor or PMOS transistor. So here over the uh, diffusion material. So we are considering a polysilicon material with red color. So over the N diffusion we are drawing a red color. So to work like as a N diffusion transistor, that means N depletion mode transistor. So for depletion mode transistor, we have over a polysilicon, we have a implant. So implant should be in yellow color. Implant, that means dotted square box line that should be indicated in yellow color. So we have to draw a dotted square box over the polysilicon material. So that will fulfill the depletion mode transistor category. That will fulfill the depletion mode category. So after that, so we have an output. So we have to connect the output. So that output will be connected at the depletion mode transistor side. So we are extended that output for the same polysilicon material for free V out, clear. So for different material, so if you are using the same material, so we need not to connect any type of connection in between one material to another material. So if we have taken two different layers, so at the time we have to show a connection. That means in metal to N diffusion, at the same time from in diffusion to output. So here for enhancement mode transistor, we are also uh, we are also uh, take a polysilicon layer, that means polysilicon material with red color. So that will be drawn over the N diffusion material to fulfill the enhancement mode transistor, to fulfill enhancement mode transistor, and finally we have to give a connection in between the that is ground and diffusion material. So this is a simple and effective stick diagram for inverter for only NMOS devices, for only NMOS devices. That means here in this NMOS technology, we are used only the NMOS transistor. So that's why vertically we have to draw an diffusion line. So over on the diffusion line, we are overimposing a polysilicon line. Overimposing a polysilicon line. Then it will be works like as a inverter, simple inverter. So this same stick diagram will be extracted in a scaling manner. Scaling for stick diagram, so we need not to use any measurements, but stick diagram. So we have to use a appropriate scaling. Scaling means so uh, for every layer we have some of the rules and regulations. So we have to maintain some lambda rules. So we will discuss that lambda rules in coming classes, but in today's class, so that will be only uh, when we are drawing a stick diagram. So that is the same implementation will be implemented with a scaling factor, and some of the indications, so we have to extend that stick diagram to the layout diagram. So clear. So here same whatever that same thing will be happened in the layout diagram. That means we have to use the metal with some indications, that is same with the blue color but straighted lines. So and for end diffusion so we have to use the green color. So over on the green color we have to uh, overimposing polysilicon over the end diffusion material. So that will be uh, considered, layout diagram will be considered with some rules and regulations. That means some scaling terms and some indications. So we extend the stick diagram to layout diagram. So the colors will be same in stick diagram and the layout diagram. So next example. So next one is a simple expression by NMOS technology. That is a two-input OR gate. A two-input, a two-input NOR gate, not OR gate. It is a NOR gate. A plus Y is equal NOR gate. Operation is A plus B whole bar. That means inverting of OR gate. So here already we see in the inverter. In case NMOS technology, for every time we have to use a pull up device as a NMOS depletion mode transistor. For any type of NMOS, if you are designing any logic expression with help of the NMOS technology or NMOS transistors. So in pull up part, we have to design depletion mode NMOS depletion mode transistor, and in down part or below part, so we have to use enhancement mode NMOS transistor. So here to implement a two input NOR gate, so we require two enhancement mode transistor. So in upper part, so we have to connect the sorry, this is not a two input NOR gate, it is a two input NAND. So here that operation is A.B whole bar. So it is a two input NAND gate. So in case two input NAND gate means, so if you are connecting p type transistors, so if that P-type transistors are in OR functionality, so we should connect series manner. So if the P-type are and functionality, we should connect parallel. So and for NMOS, that will be reverse. So here for NMOS, if that unfunctionality, we have to connect series. For our functionality, we have to connect parallel manner. So here we now we have to see a two-input NAND gate. So that is the expression for the NAND gate is equal to y is equal to a dot b whole bar, a dot b whole bar. So here we have the dot, that means AND operation, multiplication operation in one variable to another variable. So in case of the NMOS, so we have to connect those two variables in series manner. In series manner, upper part is depletion mode transistor. Upper part is depletion mode transistor. So in the below part, so we have to implement enhancement mode transistor in series manner. So already we have the truth table. So by using the truth table, we are very familiar with the operation. So you have to see the operation. So now I will tell you how to draw a stick diagram from that transistor level diagram. So here we already designed a transistor level diagram. So here we have to draw a stick diagram. Stick diagram means, so we must and should need metals for metals for to give a proper voltage connection, that means VDD and the VSS ground levels. So in blue color, with blue color, so two lines are drawn. So and we in this overall diagram we have NMOS transistors are made up of with N diffusion. So N diffusion will be that will be marked or represent with green color. So from up to bottom, so we are drawn a green color line. We are drawn a green color line. So here we are using a different mode of transistor, that is uh, de uh, depletion mode and enhancement mode transistor. For depletion mode transistor, we have to uh, overwrite that green color with a red color, that means polysilicon, to work like as a transistor. So we must and should have two materials, that is an diffusion material and the polysilicon. Then only that will be work like as a transistor. Then only. So due to that reason, so we are overimposing that green line with red line with the red line. So here we have to for def- depletion mode transistor, we have to over implant symbol on the polysilicon. So that will be drawn with help of the yellow color with the dotted line square box. So after that we have to give two inputs for enhancement mode transistor. So for those will be connected in series manner. So that's why we are drawn that polysilicon in a series manner. Clear? So by following this one, so we have to design any type of stick diagram for we have to design any type of transistor diagram to stick diagram. So after the layout diagram, so we have to uh, draw the layout in the same manner, but with a we have to use some of the scaling factors. The scaling factors are nothing but so for metal we have to use 3 lambda is nothing but, so that is a standard consideration, standard. So in case 3 lambda is equal to, we can consider 1 centimeter or 2 centimeters or 3 like as your convenient, but whatever we are maintaining one consideration. So I'm coming to 2 lambda, so definitely that will be reduced from the 3 lambda value. For example, metal is 3 lambda, so you are considered 1 centimeter. 3 lambda is equal to 1 centimeter. So coming to diffusion, the diffusion is that is 2 lambda. That means so 2 lambda that will be 3 lambda is equal to 1 centimeter, then 2 lambda is equal to 0.5 centimeter. 0.5 centimeter. That means that variation will be shown from one layer to another layer. The variation must and should be shown the difference value in between one layer to another layer. So that is the remembering point while we are drawing the layout diagram. So and next example, it is only NMOS NOR gate. So simply in the above diagram we are connected series, but here we are connected in parallel because that will be NOR operation. A plus B whole part, that is NOR operation. So the remaining part will be, so only in the below part the diffusion material will be varies. That means parallelly we have to draw two diffusion materials. So and parallelly we have to give two inputs. Parallelly we have to give two inputs in stick diagram. So in the same layout diagram also we have to draw the same thing. So next one, so this is about the CMOS, NMOS inverter, and it is we have to see CMOS inverter. Only one inverter, CMOS inverter will be. I will explain in today's class. That is in CMOS inverter. So we have to use both the PMOS and the NMOS inverters. So to implement any type of Boolean expression in CMOS technology, so we have to use both P type and N type. So then only we get a CMOS implementation, CMOS implementation. So here in a simple CMOS inverter, it is the combination of both PMOS transistor and NMOS. So in pull-up part, we have PMOS transistor. In pull-down part, we have NMOS transistor. So the same thing will be drawn in stick diagram. Stick diagram. That means, so for VDD and VSS, we have taken metal contacts. So after that, for PMOS type transistor, so we have to use P diffusion material. So here P diffusion material is P diffusion material is that will be represented with yellow color. P diffusion with yellow color, so yellow color will be taken, and NMOS diffusion and diffusion green color is taken. And for those two transistors, either it may be P diffusion or N diffusion. So if that will be work like as a polysilicon, so then we have to overimpose and the common input. So that's why we are overimposing that polysilicon color, and that will be extracted to input. The same thing will be taken. So if we are not taken the same input, so we have to take any type of extraction. That means we should place a contact in between polysilicon to metal, and we have to apply the V input. So to reduce extra connection, to reducing the extra connection, so simply we are using the same material. To if we are using the same material that represents electrical contact, so we need not to connect an extra connection with those materials. So for output, so we are connecting that's two colors with metal, that is a blue color, and that will be extended to V out. That same thing will be extended to V out. So this is we have to draw a stick and layout diagram for any type of MOS transistor, and this is about today's class. So we have to see remaining topics and the concepts in the next class. So these are so some of the layout rules. So we'll discuss in tomorrow's class. So so that is about today's class. So we have if you have any possibility, so you have to practice with in Pucknell book. So in Pucknell book, you have to see these layout and layout diagrams and the stick diagrams. So first you have to design, you have to take a Boolean expression. So by seeing that Boolean expression, first of all, design a transistor diagram. So after that, you have to draw a stick diagram. After that, a stick diagram with colors. So with colors. So you have to do practice with colors. So then only you are very convenient or very effectively you have to draw in examination. So without practicing, so just seeing and going, and that is not implemented uh, in this subject, or in this especially in this session. That means while we are learning the stick diagram and the layout diagram, so must and should we have to work with pencil. We have to work and practice with pencil. So then only we have to you are very efficiently drawn in the examination. So you have otherwise at the last pages of the Bucknell book, at the last pages, so you also see different stick diagrams and the layout diagrams. So you'll see and observe and first understand the diagrams. So after that you have to do practice with we have do practice with the pencil. So without practice, you can't draw the stick diagrams and the layout diagrams. Clear? So you must and should practice with pencil, with color pencils. So then only you are very comfortable, and you must you effectively learn the concept. Okay, my thank you, everyone. I will continue the remaining topics in next class.